Okay, hi everyone, thanks for coming. So this is joint work with Nisarg Shah, who's here and is now at Toronto, and Kamesh Munagala, who's also at Duke. I'm Brandon. So there are three things that I want to give you in this talk. The first of the three things is sort of a very general framework for thinking about public good allocation problems that generalizes a lot of the existing frameworks for thinking about how to pose the problems. Okay? The second thing I'd like to give you is a good fairness guarantee. Just get it loud. The second thing I'd like to give you is a good fairness guarantee in order to work with in this kind of a domain in this very generalized setting for public good allocation problems that I'll talk about. And then the final thing that I want to do is give you a little bit of the idea behind the algorithms that we were able to give in this paper for computing approximate solutions to that concept of fairness. Okay, so that'll be kind of the outline. So first, let me tell you about the model. So you need to know what an indivisible public good is. Fortunately, people have already defined for me what indivisible goods are, and we'll be in this same setting. But you can think generally about resource allocation problems as fitting into something on this 2x2 chart. Okay? So we've already discussed indivisible versus divisible goods, but actually what I'm interested in is sort of that right column of public goods. These are different than private goods in that we no longer think about assigning a good to an agent and no one else gets anything out of that except for the agent to whom it's assigned. Instead, we think about public goods as being things like, do I or do I not build a road? This potentially is a resource that's shared among many agents and provides utility to many agents simultaneously. Okay? So this will be the sort of square that we'll be in for the remainder of this talk. More generally, you could frame this kind of mathematically by saying we have some set N of N agents and some set M of M public goods. So far, nothing weird or strange. Okay? The strangeness comes in at this step, where now we say that a feasible outcome in a problem like this is actually a subset of M, a subset of the public goods that we're choosing to allocate. Okay? This is different than private goods because in private goods, an allocation itself is a matching, right? So it's sort of a very different combinatorial structure behind a solution here. And in general, we'll differentiate the kinds of instances of problems by the sets of constraints that some feasibility set is allowed to use. Okay? So you can think of this set F being all the sets of feasible outcomes, and then my results will be differentiated based on what kinds of constraints are necessary to write that set F. So we'll talk more about this. Agents will just have additive utility, so nothing complicated going on there. So for every public good, agent I will have some utility uij, and I'll assume that their utility is additive across the public goods, so that their utility is just the sum over the goods in the set that we choose. Also, I want to mention that I'm going to, throughout this talk, normalize the maximum utility for an individual public good to be 1. So anywhere you see like a 1 or a 2 or a constant like that, that's what 1 means. Okay? So in particular, note that does not mean that I'm normalizing the utility of an agent for an outcome, for a whole set of public goods to be 1, just for an individual public good. Okay, so F can represent a lot of different things. It's some set that corresponds to the kinds of feasible outcomes. There are two classes that I'll consider in this talk. The first is when F represents matroids. That is to say, when you could write the feasibility set in terms of some matroid constraints on the ground set of public goods. Okay? What kinds of applications or problems might that model that you would care about? Well, I have two good examples, and then maybe you can give me more examples after this talk. So one good example is if you're interested in social choice. Okay? So any kind of a social choice problem where you're trying to select, say, k candidates out of some potential list of candidates, that's the multi-winner election problem, can be represented where the individual candidates are public goods, and you have some matroid constraints that say represent you must choose k of them, something like this. Also, the public decision-making framework, which was introduced in EC here last year by Konitzer et al., used a public decision-making framework to talk about the allocation of public goods. That setting can also be described by matroid constraints. In that setting, you think about there are some sort of number of referendums, so some number of issues that we have to come to some decision on. Okay? And for each of those issues, you have to decide on exactly one alternative. So you should think of this as like we're taking a vote, and there are 10 issues on the ballot, and a final decision has to be reached on each one of these 10 issues. Can also be represented with matroids. The second major class of constraints we consider are packing constraints. So this is where each of the public goods has some sort of associated cost, or maybe a vector of costs, and your constraints are packing inequalities on those costs. Okay? And the canonical problem for this set of constraints would be participatory budgeting. This is the kind of model where you say just have a single budgetary constraint and people vote among some set of projects on which they would like to see implemented in their local community. Okay? So these are some application domains. I would love to hear more. Let me tell you now about the second thing that I promised to contribute. So that was the general framework for thinking about public good allocation problems. It generalizes a lot of existing ways of thinking about these problems. Here now is the fairness idea. The first thing you might try to do is like in the previous talk, and I believe in the next talk as well, to think about envy. But it won't take you long to realize that envy is not entirely well defined for public goods, right? Because the actual allocation I choose now is just a set that's common to all agents. The idea is I'm choosing goods that are shared among all the agents. So there's no meaningful notion of my allocation versus your allocation. So instead, we'll go to the next most natural fairness guarantee, that is proportionality, where every agent expects to get 1/n of their utility from their favorite outcome, right? Their best possible outcome. And you might say, okay, well, I'd like to provide some kind of a guarantee like this for public goods, because at least that makes sense as a guarantee. What I want to tell you now is that there are a couple of subtleties here. On the one hand, proportionality is too strong of a guarantee, in the sense that it will be very difficult to provide it or any approximation. On the other hand, it's too weak of a guarantee. And this has to do with the shared quality of public goods. And the combination of these two things will lead us to modify our approach and think about a new fairness guarantee. Okay? So first, proportionality is too strong. Well, why is that? Consider this is sort of a public decision-making kind of a thing. We have two agents, and we have a single issue, and we must decide yes or no on the single issue, and the agents have opposite preferences. You think about it for 5 seconds, and you realize, wait a minute, that's just a private good. And of course, Konitzer et al. Observed this in their paper last year, that in fact the public decision-making framework generalizes all private good allocation problems. And so you can't give any kind of a multiplicative approximation to proportionality in this public good setting that we're considering, for exactly the same reasons that you can't for private goods. Okay, so I won't belabor the point. The fix, of course, is that you need to consider additive approximations, as Seth was just telling us about, right? You have to consider things of the nature, envy freeness up to 1 kind of things. Those are sort of fundamentally additive guarantees. In that context, it was framed in terms of like swapping one good, but you could instead think of it in terms of an additive approximation on utility, and that's the approach that I will take in the remainder of this talk. This is basically inspired, again, by the idea of Konitzer et al., where they proved that in the public decision-making framework, there's always an outcome that gives every agent within 1 of their proportional share. They actually proved something stronger. It's more like the envy freeness up to 1 guarantee, but I don't want to get into the subtleties at this point. Okay? So we can fix that problem, the problem that proportionality is too strong. You need to essentially just think of a different approximation. But the other problem is a little bit more interesting. In some sense, proportionality is too weak. So here, what you should think of is just blowing up that example I was just giving you. So I'm just cloning Alice n over 2 times, and I'm cloning Bob n over 2 times, and I'm cloning the issue m times. Okay, so I'm just blowing it up. But think about there being many, many more agents in this problem than there are public goods. But there are still many public goods, maybe like 1,000, and maybe like, I don't know, 1 million agents or something like that who are voting in this. The problem here is that if I think about the proportional guarantee, it's just m over n for each agent. But if m is a lot bigger than n, and note that that's, if other way around, if n is a lot bigger than m, and that's a natural setting for a lot of voting type problems, right? Then this guarantee is essentially nothing, right? And that seems intuitively wrong, because in an example like this, actually I could give m over 2 utility to every agent. In fact, n shouldn't even appear in the guarantee I give on an instance of this type. And the reason is that the agents are very well partitioned into coalitions who have exactly identical preferences. And so somehow what proportionality is not capturing is the possibility of sharing between agents, and the fact that our guarantee should somehow reflect that this is a possibility when we have public goods. Okay? That's going to be exactly the kind of approach that we take to sort of fixing this problem. So instead of trying to define proportionality only on individual agents, we're going to define it on every subset of agents. So for every subset of agents, I want to say that they should get their proportional share, that is to say, size of that coalition over the number of agents, of their best outcome. Right? So this would be if you just strictly tried to write down what a generalization of the idea would be. But of course, the problem is, what the heck do we mean by the best outcome for a coalition, right? That in that previous example, the agents agreed, but that need not be the case in general. A coalition might widely disagree, and we want to provide a guarantee for every possible coalition, not just the ones that say agree exactly on what they want or agree closely on what they want, something of this nature. So how would we do this? The key answer of this paper from the second part for how to define fairness is don't do it. Don't at all try. Okay? Instead, we'll provide a guarantee for all coalitions for all possible outcomes that they might consider. Okay? So we'll just give something strictly greater and completely avoid the problem of trying to define that strange thing. In particular, this is the definition of fairness that we'll use. This is an adaptation of the idea of core from classical economic literature, slightly rephrased and redone in subtle ways for this particular problem. Okay? So what we're going to consider is that we've sort of failed for a coalition of agents. If that coalition of agents could come up with any other outcome, right, such that when their utility for that other outcome is scaled down by the proportional size of that coalition, every single agent in that coalition would still prefer that other outcome to the outcome we proposed. Okay? If that's the case, we say this is a bad coalition, a blocking coalition in some sense, and our goal will be to find an outcome that has no blocking coalitions, right? That is stable to these kinds of sort of proportionality violations for every possible coalition, for every possible outcome. All right? And that's what we'll mean by a core outcome, one that doesn't have any such blocking coalitions, and this will be our target and our goal. In particular, it implies proportionality in the standard sense. Just consider coalitions of size 1, right? And it'll be exactly the same definition. It implies Pareto optimality if you consider the grand coalition of all possible agents and just plug that in. But it also gives you this kind of proportionality guarantee for all coalitions who might possibly share resources in between the singletons and the grand coalition. Okay, so this is our target. Of course, you might think, if it generalizes proportionality, it's going to be hard for the same reasons as proportionality, and you're exactly right. So we will again talk about approximations, and we will again need an additive approximation, just like in proportionality. So in particular, we'll use a bicriteria approximation. We'll give ourselves a delta multiplicative slack, so this is the 1 plus delta term up there, and then we'll also give ourselves an alpha additive slack. Okay? But otherwise, this is just the same definition with those slacks. And you might think, okay, well now we're approximating the core versus approximating proportionality. What's the point? The point is that on those kinds of examples I showed you before, where there's large opportunity for sharing among coalitions, a small additive approximation remains meaningful in such a setting, whereas a small additive approximation to proportionality may not remain meaningful. Okay? So our questions then, I've now defined for you, this is my second thing I wanted to tell you, which was about a really cool new idea for thinking about fairness in these kinds of public good settings. The last thing I want to do for you is talk about the major technical questions we address in the paper. Do good approximations to this objective exist? It's not obvious that they do. And can we compute them? Okay? In particular, do good integer approximations exist, right? We're in the indivisible good setting. There's a lot of work on if you're allowed to give fractional allocations. Okay, so this is what we're going to address in the remainder of our time. So let me show you our results here. As I said, they're differentiated based on the kinds of constraints that your set F is allowed to encode. All of our upper bounds are constructive, so we have polynomial time algorithms for these bounds, and the lower bounds are existential. They're not based on computational hardness or anything like that. Okay? So the first result from Matroid, which is kind of the easier one, so this is multi-winner elections, public decision-making, that sort of thing, is we can give an algorithmic result that gives you a 0,2 approximation. So there's no multiplicative slack in this whatsoever, and we just need an additive 2, whereas remember that for proportionality, we had an additive term of like 1 or something like this. So we're quite close to the same additive term that one gives for NV freeness or for proportionality, but we're giving it for every possible coalition who might deviate. It was sort of actually surprising to us that we were able to give such a guarantee. So I just want to stress that. That was like, we weren't exactly expecting that. It was kind of cool. There's a lower bound that says you need an additive approximation here. It's absolutely necessary. It's not too hard to see where one might come up with this. But then the more interesting and technical work happens for packing constraints. So this is somewhat more challenging to give an algorithm for. The lower bound is not that much stronger. Okay? We're able to prove you need a multiplicative slack if you're going to do packing constraints. That's necessary. But then the upper bound we're able to give has this logarithmic term in the additive approximation that's sort of strange. So this, I'm hiding a few things under the big O tilde, but really the dominating and the important thing is the log r, where r is this very strange quantity that I'll try to explain to you. So think about the following fractional allocation. What if I was to try to compute an allocation, a fractional allocation, that would give to every agent as large a fraction of her total possible utility from a feasible outcome as I possibly could? So it's like an egalitarian solution, except it's egalitarian on shares or fractions of your maximum possible utility rather than on some absolute scale or something like this. Okay? Whatever that fraction is, that max-min fraction you're able to get, that's R. So if you're ever able to give to every agent with a fractional outcome 1/3 of their maximum possible utility, then R is 3. Okay? And our additive term depends logarithmically on R. All right? So these are the basic ideas of the results, and I'll show you in just a couple of slides some of the high-level ideas of how you might accomplish these. For matroids, the algorithm is not too hard to understand. The first thing that one might think, especially if you're familiar with this literature and some of this other work using the Nash social welfare, is we should maximize the Nash social welfare, shouldn't we? And we tried that. So this is a good way to start, is to think, well, let me just choose the outcome, the integer outcome that maximizes the Nash social welfare. Okay? This is a hard problem, but maybe it'll show me something existential. In fact, not quite. And the reason is actually fairly easy to see. If I give any agent 0 utility, then that objective will go to -infinity, which means that this algorithm will always do anything in its power to avoid giving any agent 0 utility. And you can construct examples that exploit that fact of the algorithm, where essentially the algorithm will try to satisfy a small number of agents by giving them non-zero utility. In the process, we'll sacrifice the utility of an extraordinarily large fraction of the agents, and you'll get a very non-trivial approximation, a very trivial approximation to the core, right? Something that like depends on the number of public goods you're allocating and is effectively not much of a guarantee. So that won't quite work, but it's still basically the right idea. Okay, so this is the first thing, which is that instead, we just smooth a little bit. Okay, so we essentially redefine an objective based on other work that's been done that is just explicitly trying to deal with the zeros issue. Just add a 1, where remember how 1 has been normalized to the maximum utility for a single public good, inside of the log, so that you stop worrying so much about those 0 utility agents, effectively, but you're still maximizing some concave thing, and it's still fair in some sense. What we're able to prove is that, in fact, if you can find the optimal solution to that program, the smooth Nash welfare, then it's a 0,2 core approximation for any of these problems that can be defined in terms of matroid constraints. Okay? You might think this is unsatisfying. I told you I would give you algorithmic results, but of course, maximizing that objective is still hard. So what we're able to show in the paper is that, in fact, a local optimum is sufficient for that guarantee. Actually, the proof that that gives you a 0,2 core solution only needs a local optimum. It doesn't actually need the global optimum. And you can find a local optimum to this program in polynomial time using the local search algorithm. Okay? So that's the basic idea behind the matroid algorithm. For packing constraints, it's somewhat more complicated. I don't want to go into the details, but basically we have these 2 different fractional allocations. X is just the fractional max Nash welfare solution, and Y is this strange thing I told you before, this maximally proportionally fair allocation, et cetera, et cetera. We mix these 2 and we round them in some way that is sort of painfully technical, even from our perspective, and we're able to get the guarantee that I promised you doing that. Okay? This is not an expectation. We have an algorithm that with constant probability gives you an outcome satisfying this, so you run it some number of times and you get one, right? Okay. We're able to give bounds on R. In particular, it's no more than M, it's no more than N, and there are other bounds on R in the paper. It can be substantially better than M or N. So this is kind of a logarithmic result, but kind of not, in a way that's a little bit too subtle for me to present in 5 seconds. Some open questions that I do really want to get into. First is motivated by what I just told you, which is, can we do something better here? None of us are convinced that that logarithmic result for packing constraints that I just gave you is really the right answer, and the gap between that upper and lower bound should indicate this. And so this is one interesting open problem. Is there a better algorithm to give you a better upper bound, or some impossibility behind that? We don't know. Our second question is maybe we should change the sort of model, change the kind of fairness guarantee we consider. In classical economics, you don't think about scaling down the utility of an agent. You think about agents coming into the system with some sense of endowment, some number of resources to which they are entitled, and you think about considering scaling down the endowment of a coalition, but then not scaling down their utility. Okay? So this is a somewhat different model, so I don't want to describe it in detail here, but there are some problems in our community and other related communities where it seems like maybe there's a connection to that's closer to this kind of a core guarantee. For example, in some of the proportional justified representation literature, there's this connection that seems to be there between the two, and we can't quite pin it down, but we suspect it's related to this notion. And finally, I'm personally very interested in other applications where fairness on coalitions really seems like the right thing to do and the right question to ask. And so if any of you have those applications in mind, please come talk to me. I would love to hear from you. Thanks, guys.
One quick question. Well, the next speaker, please pick yourself up.
So the question is for divisible items. So you might correct it. So it's a new notion and you're going directly for divisible items. For divisible, is it easy to justify this proportionalized proportionality, or maybe randomizing already a lot of trivial, or is it still an interesting question?
So for divisible outcomes, if that's allowed, just maximize the Nash welfare. You can do it in polynomial time, and it'll give you an exact core outcome. And so that's why we've sort of jumped ahead. You're exactly right. Yeah, it's essentially an easy problem. There is some previous work that we've worked on, actually, so if you are interested in divisible outcomes, but your utility model is more interesting, then all of a sudden it becomes an interesting algorithmic problem. Can you maximize it if you, say, have general concave utility functions? That no longer is entirely clear whether you can find the right program, because you don't want to maximize just the Nash social welfare if you have more general concave utility functions. But under some settings, I can come up with transformations where you can still compute exact cores in polynomial time. But for the more general setting of just arbitrary concave utility functions, we don't quite know. Any other questions?
Thank you.